expansion or multi-stage expansion in turbine with reheat, and the second modification made is to have multi-stage compression with intercooler or with intercooling process. So that is what we have looked last week. So what are we going to do right now is to continue with our problem. This problem is basically I took from the test to question 14.15.02. Okay. So let us analyze the question first. That I mentioned before, the most important thing for a gas turbine plant, in order to look to the solution or to analyze the problem, the first thing that we need to know or we need to do is to look at the schematic diagram. After that, when we have completed the schematic diagram, then we have to read back the question and make sure that we have the same configuration or the same layout of the plant what is being described with the question. And then only we are going to look at the TS diagram. Okay, so let us look into this case. A gas turbine plant consists of two-stage compressors with an intercooler between stages. So right now, it already stated we have two compressor and intercooler, right, in between stages. And then we have two combustion chambers, meaning that possibility of having reheat, multi-stage expansion, because we have two combustion chamber. And then two-stage turbines, of course, it's already been cleared there. We have two turbine. And then, of course, what we have learned for intercooler is referring to the compression process, and the extra combustion chamber is referring to the reheat process. Then we have an electric generator. The high pressure turbine drives the high pressure compressor, and the low pressure turbine drives the low pressure compressor and electric generator. So we have two drive, or we have two shaft. One shaft is to be used by the high pressure turbine to run the high pressure compressor, and we have the second shaft being described that run by the low pressure turbine, which drive the low pressure compressor and electric generator. So if we can indicate right here, high pressure turbine drive high pressure compressor. That's it. Only one statement about the high pressure turbine and the high pressure compressor. And the next statement is basically on the low pressure turbine being said to drive the low pressure compressor and electric generator. So right now, what we could sketch is the two shaft. What drive, which turbine drive which component? So we have the high pressure compressor attached to the high pressure turbine, and this is the only description give about which turbine drive which component. Okay, so the high pressure turbine in this case will run the high pressure compressor. And then we have another shaft And we attach this shaft with 3 components. One is the low pressure turbine, run by the low pressure, high pressure compressor, low pressure compressor, run by the low pressure turbine, and the low pressure turbine also driving an electric generator. So this is what being said. So this is the compressor for low pressure. This is turbine for the low pressure. And this is our electrical generator as the power output or the W net of this plant. And we know that the modification made to this plant is either using intercooler or using reheat. And in this case, we can see that there an intercooler. So usually intercooler will incorporate the compression side. So what we have right here for the compressor low pressure, we are going to take the air from the ambient or the surrounding. So this is the intake. And then we are going to have the compression process. And also we are going to incorporate with an intercooler before entering to the high pressure turbine. So this is the intercooler. So this compressed air will be cooled in the intercooler. So this is our intercooler. Okay, let's say this is IC intercooler. So we have already completed the intercooler. The two-stage compression process, which we have stated there, the low pressure compressor and also the high pressure compressor. Okay, and then we need to put the combustion chamber. So if you can look right here, the place that we are having high temperature, which is the maximum temperature of 800. Therefore, this being said that the maximum, right? And then we have another temperature which is 750. And this 750 is mentioned for the second combustion chamber, right? So if second combustion chamber, meaning that there is a reheat, and this particular temperature 750 is for the reheat process. Therefore, when exhausting the combustion gas from the first turbine, which is the high pressure turbine, we are going to have another combustion chamber before entering the low pressure turbine, and this should be the temperature of 750. And therefore, the 800 degrees C should be the temperature before entering the first turbine, which is the turbine high pressure and referred as the maximum cycle temperature. Therefore, we have the first combustion chamber should be located before entering the high pressure turbine. Of course, the last compressor will be used to compress the air and entering the first combustion chamber. Okay, if I complete the flow direction, in this case, after the low pressure turbine, we are going to have our exhaust condition. Of course, this is the first, this is the second flow, this should be the third flow. And we can put right here, this is our combustion chamber number 2. This is our combustion chamber number 1. Okay? Then what we do, we are thinking that our flow is completed. Then what we do next is to read again the question. And make sure that what we read again the second time should reflect what we have sketched right here. Okay, so let us read again. A gas turbine plant consists of two-stage compressor. So one first stage, second stage. So the compressor side is complete. And then with intercooler in between, we have one intercooler right here. Two combustion chambers, CC1, CC2. And then we have two-stage turbine, 1, 2. And we have electrical generator. This is our electrical generator. So high pressure turbine, compressor completed, turbine completed, low pressure turbine drive the low pressure compressor. So low pressure turbine run by the running the compressor low pressure and also an electrical generator. Okay, and the first turbine will run the compressor high pressure, which been described right here. The turbine drive the low pressure compressor. And then now we try to look at all the parameters given. So atmospheric and air enters the compressor at 30 degrees C. So this should be our T1. Okay, our T1. So let's say this is our state 1. Let's put our state 2. This is our state 3. This is our state 4. This is 5. And this is 6. And then this is 7. And then this should be number 8. Okay. So meaning that we have 8 states. Okay, 8 states. Now the 30 degrees C is state as intake, 30 degrees C. And then the overall pressure ratio is 9.5/1. So what is the overall pressure ratio? The maximum pressure divided by the minimum pressure. So this is the intake of our low pressure compressor, should be our ambient condition. So meaning that this is the minimum. So P1 should be our minimum pressure. And the maximum pressure is the last or the exit pressure after the last compressor. So in this case is P4. Right? So this is P4. If we look at the compressor side. If we look at the turbine side, again, the 8 should be the lowest pressure. This is P8. And the highest pressure of the turbine is usually before entering the first compressor, the first turbine, which will be equal to the pressure of the high pressure compressor. So this should be our P5. And this is 9.5/1. Okay. And then the maximum cycle temperature 800 should be at T5. This is T5 maximum. 800 degrees C. And then the 750 second combustion chamber will raises the gas temperature to 750. So meaning that this 750 is describing the temperature of the combustion gases after the second combustion chamber, which is T7. So this is T7, which is equal to 750 degrees C. Okay? And then each compressor has the same pressure ratio and the intercooling is complete. So if the compressor have same pressure ratio, meaning that the P2 over P1 is equal to P4 over P3. So same pressure ratio for compression process. So P2 over P1 is equal to P4 over P3. Okay? And from this information, we could also write the relationship between the pressure ratio. Okay, the relationship between the pressure ratio. So we have the P4 over P1, which is the overall pressure ratio. P4 over P1 is equal to the pressure ratio of the low pressure turbine, or low pressure compressor, and this is multiplied by P4 over P3. You see, the 2 and 3, the pressure of 2 and 3, assuming there is no pressure loss at the intercooler, meaning that the P3 and P2 is equal. So we can cancel this off, right? So what is left is P4 over P1, which is equal to the overall pressure ratio. And you know that a P2 over P1 is equal, then we can write this as a P2 over P1 squared. Okay, that is the extra information from the case of same pressure ratio. Then we are getting the description of the intercooler, and it's been said that same pressure ratio, complete intercooling. So if complete intercooling, the meaning of complete intercooling is the temperature enters each compressor, they are the same. So temperature enters the compressor T1, the temperature enters the compressor, each compressor, this is T3, meaning that complete intercooling will give us T1 equal to T3. Okay, so T1 is equal to T3. With these two information, same pressure ratio and complete intercooling, so what we are going to have right here is the W compressor should be the W minimum. Okay, so this is the summation or the work input to the compressor should be minimum. Right? Okay. And then we have the isentropic efficiency for each compressor stage, high pressure, low pressure turbine as 0.8, 0.83, and 0.85. Meaning that apart from we have the 8 states, okay, 8 states, we are also having extra temperature that we have to look for because of this isentropic efficiency. So the extra temperatures or the extra state that we have to look for is particularly for the low pressure compressor. We need to define what is T2S. As for the compressor high pressure, we need to define what is T4S. For the high pressure turbine, we need to define the T6S. And lastly, for the turbine low pressure, we need to define what is our T8S. So these are the extra state that we have to get in order to get whether to get the T4, T6, T8, or T2. Okay? So meaning that if we look right here, we have 8 states. But as far as the temperature is concerned, because of the isentropic efficiency, we have to add 4 more temperature. So in total, the states that we have right here is 12. Okay, it's 12. Any question, guys, right now? Any question, guys?
So far, okay, sir.
Okay. So neglect mass of fuel, neglect pressure losses for the both combustion chamber and also the intercooler, and neglect the changes of kinetic energy and potential energy. Meaning that what we are having right here, just the Q, W, and also the for both for the compressor and also for the turbine, the W for compressor and turbine, and the Q for the combustion chamber number 1 and combustion chamber number 2. Okay? So is there any mechanical efficiency? Oh, there's no mechanical efficiency, so that will make our work easy. Okay? Right. So right now, we also can write the work relationship between the shaft. Okay, work relationship between the shaft. What we could have right here is the compressor 3-4. The W34 we can write as equal to the W for turbine, in this case W56. And also we could write, as for this second shaft, we could write the W net. What is the W net? The W net, which is the W for the electrical generator, equal to the W for the turbine low pressure 7-8 minus the W for the high pressure compressor, which is the W12. So as far as the work relationship is concerned, looking at the shaft, which turbine drive which components, then we could write the first equation and the second equation. Okay? So after saying that, what we are going to do right now is to sketch our TS diagram. So, of course, the first pressure that we could sketch is the overall pressure ratio. So this is our overall pressure ratio. Sorry. This is our overall pressure ratio. We have 2 intermediate pressure. Okay, and when you sketch these 2 intermediate pressure, be careful. Don't ever connect the pressure ratio, the intermediate pressure ratio for the compressor side and the turbine side, unless the question says so. Okay, I repeat again, never connect the intermediate pressure for the compressor and also the intermediate pressure for the turbine unless if the question said so. In this question, there's nothing mentioned on these two intermediate pressure. Therefore, you are going to sketch separate pressure ratio. But what you have, the information, is for the compressor, the pressure ratio, they are the same. Okay, so this is the intermediate pressure for the compressor, and this is the intermediate pressure for the turbine. But nothing mentioned on the turbine side. So we just sketch one line which representing the intermediate pressure in between the first stage of the turbine and the second stage of the turbine. And then remember that we have the intercooler. Okay, intercooling process will give us the same intake temperature of the compressor. So let us sketch the compression process. So compression process, isentropic efficiency. And then we have intercooling. So intercooling will start from this point. Intercooling up to here. Okay, you see, this is 1, this is 3. Okay, due to the same isentropic efficiency, complete intercooling, same pressure ratio, what we are going to have for the second compression process, the temperature will be the same. Okay, for the outlet of the first compressor and the outlet condition of the second compressor, they should be the same due to the complete intercooling and same pressure ratio. Meaning that if this is 2S, this is 2. This is 4S, this is 4. Okay? Remember, from here, we are having the T1 is equal to T3. We are having the T2 is equal to the T4. And this T4S or the T2S equal to T2. Sorry. T4S equal to T2S. T2S equal to T4S. Okay? And please remember, they are equal because of complete intercooling, same pressure ratio, and they are having same isentropic efficiency for both compressor. That's why we have this information. If you are not sure, right? If you're not sure, you can do it one by one. We will look after this. Right? Let's say we are not sure. Then we have to look individually whether we are going to have the same temperature or not. Okay? So this is at the compressor side. And then as for the turbine side, so this should be our first expansion process. And the maximum temperature is going to be number 5. So this is 6S, and this is 6. And then we are going to have reheat in the second combustion chamber, and the temperature is not the same as the T5, a bit lower. So let's say this is the temperature. So the beginning of the heat supply in the combustion chamber number 2 is from 6 up to 7. So this is our state 7. And then we have our second expansion process, isentropic, 8S, actual expansion with isentropic efficiency. So this is 8. Right? So look here, the beginning at the combustion chamber number 1, the beginning of heat supply is from 4. Up to 5. So this is at CC1. This is at CC2. Of course, this is the first compression process, low pressure, high pressure compressor. This is for the high pressure turbine. This is for the expansion for low temperature turbine, low pressure turbine. So what is the exhaust gas? The exhaust gas is the T8. Okay. So what we have to do right now to complete it with the direction of the process. Okay. So we have 4 states right here. 1, 2, 3. So there are 6 states. 1, 2, S2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have total 12 temperature that we need to get it. Okay. So let us have a glance. What is actually the question asked for? Oh, we haven't looked at any question yet. Okay. So just description of this question or the plan. Not yet looking at what the question asked for. So what are we going to do right now? Okay. So guys, please get ready with your calculator. We are going to get all the temperature. Okay. So T1 given. T2. We are going to get T2 or T2S. Guys. Guys. Hello.
T2S, Doctor.
Okay. So T1. We know T1, right? T1 is equal to T?
3.
T2, 3. Okay. In Kelvin, this is equal to 303. T2. T2S is equal to T1 P2 over P1 gamma gamma for gas or gamma for air? Air. Divided by gamma air minus 1. So how much is that? Before that, we need to know what is our P2 over P1. The information that we have right here is P2 over P1 is equal to overall pressure ratio, P4 over P1 square root. What is this value? P2 over P1. Any value, guys? P2 over P1?
3.082, doctor.
3.082.
Can anyone verify that?
Okay, can we verify?
Got the same answer.
All right, thank you. Therefore, T2S T2S
Doctor, sorry to interrupt. I just realized that the chat is not available.
the what?
The WebEx chat is not available.
Webex chat is not available.
Yeah, like remember like last time the setting, doctor?
No, I have unchecked everything. Once you have advised me, what I have did is to make sure that the chat is on by unchecking all the. Tak apa. Let me look at the back again. Participant. Where is participant? Where is the This is the participant. Where is the where is it? Sorry. Let me unshare because I need that command. Stop sharing first. Participant assign privileges. Yeah, I already uncheck all.
I think you need to check it, doctor.
Huh? Check it or uncheck? Just previously uncheck.
Try checking it, doctor. Taking it.
Okay. I don't know what happened. Suddenly, the check box showing me a dash. Everything is dash. And now everything is unchecked. Okay, I try. I try to write something at the chat.
Still cannot, doctor.
Huh?
Still
Are you
cannot.
sure?
Yeah.
Alamak. Get my chat?
Okay, now can, doctor.
Hmm.
Wait.
Wait.
Oh, that's you actually. No,
Right,
for us
fine.
cannot, doctor.
Right?
Still cannot, doctor.
Still cannot.
Yeah.
Okay, I try to check all. Apply.
Yeah, now can, doctor. Need to be
Okay.
checked.
Huh? Oh, check or uncheck? There you are.
Need to. I think need to check,
I
doctor.
need to check all.
Yeah.
Okay lah. Sorry lah, because of my bad lah. I don't know anything on this webback. I just use it. Eh?
It's okay, doctor. Thank you so much, doctor. Sorry to interrupt.
So please lah, anything just let me know. Nanti ada yang tak dapat nak respond. Okay, guys. Everyone can have a chat, or anyone if have this right answer, please. Okay, what is the T2S?
Doctor, for the game, gamma value, what value should we use, Doctor?
Use for air as usual is 1.4. And
Oh, okay.
for idle gas, use 1.333.
Right, Doctor.
Okay, that is the usual value that we are using for the gamma air and gamma for idle gas, for combustion gases. For air is 1.4, take note. And as for the gas, you use as 1.33.
I got 15576.
What 155? T to S.
Yeah, but it's a bit too high, Doctor.
You sure? Oh, sorry, I have the am I writing the wrong equation right here? It's gamma minus 1, right? Wrong, it's wrong. Check the equation. Gamma minus 1 over gamma, right?
Gamma minus 1.
Gamma A minus 1 divided by gamma A. I got the wrong equation for the power.
I got 417.94.
Okay, 417.9. Right? And then after that, we are going to use the equation of isentropic efficiency for the compressor. For the first stage is the T2 minus T1 divided by T2 minus T1. Okay. Which one minus which one? Where is the shorter line? The shorter line should be the T2S. The longer line is T2. Okay? So if you refer to TS diagram, the shorter line should be T2S minus T1, and the longer line is T2 minus T1. So from here, you will get your T2. Anyone? T2? Guys, please we do it together Jangan tiwa je buat seorang.
446.6.
446.6. 446.6. Alright. So we have finished with T1 and T2S. Then next is what? T3, right? You see, your T3 is equal to T1, correct? Then what we get for the T4S, you see, you try to look at this first, okay? Okay. T4S is equal to T3 P4 over P3. This is gamma A minus 1 divided by gamma A. Now, What is your T3? T3 is equal to T1. What is for P4 over P3? P4 over P3 is equal to P2 over P1. You see? P4 over P3 equal to P2 over P1. Therefore, what are we getting right here? If you put the same figures, you are getting the same value as T2S. Okay. And then after that, you are going to have the same isentropic efficiency for compressor. As for the high pressure compressor, the shorter line, T4 minus T3 divided by T4 minus T3. And then we look, the shorter line is T4S. T4S is equal to T2S, equal to T2S. T3 is equal to T1. T4 is equal to T2. And T3 equal to T1. Therefore, here you are getting the T4 is equal to T2. That is what I mentioned before this. Complete compression ratio, complete intercooling, same pressure ratio, same, okay? Same isentropic efficiency. What you will end up is your T4 equal to T2, T4S equal to T3. And because we know that complete intercooling, T3 equal to T1. So meaning that we have automatically, for this case, we have the 3 temperature of 4S and also 4. Okay? So it's up to you. If you don't understand, do it individually. This is only for the case of what? The case of the 3 things that I mentioned before this. Same pressure ratio, complete intercooling, same isentropic efficiency. If there are difference, then you need to calculate individually what I have written right here. Okay? Right. Any question?
Okay, doctor.
So you need to put something there, okay? Take note. And then after that, we are going to have our, after T4S is T5. And this T5 is given as the maximum temperature cycle. Okay? And this T5, how much is that? How much is T5, remember? 800, right? So it's 1073 in Kelvin. Okay. Now, we are going to get T6 or T6S? Refer to your TX diagram. Are we going to have T6 or T6S? What do you think? Can we have T6? Or we could have T6S. See, let me put this way. Maybe we try to write T6S first. What is T6S? This is equal to T5 P6 over P5. And this is gamma gas minus 1 divided by gamma gas. Okay. We have our T5. But in this case, how about our P6 over P5? It's not mentioned in the question about the pressure ratio of the turbine. So this is unknown. So meaning that this T6S, we have to keep in view. You cannot solve it because we don't know P6 over P5. Okay? Then what we do, we try to look the relationship between the shaft. You see this shaft? This shaft. Work for the 3/4 equal to work 4/5/6. So we have here work 5/6 equal to work 3/4, because we know that the high pressure turbine is running the compressor. So when we put the equation of CPG T5 minus T6, this is equal to CPA T4 minus T3. And if we analyze all the value, from here, it left us with T6. Therefore, by using this equation, we are going to solve for T6. Okay? So please calculate the T6. Okay, anyone? Yeah, T6, please. T6. Kat berapa tadi?
CPG ni value apa sih?
Ya.
CPG and CPA.
Take your CPG right here, take as a 1.14. And the CPA take as 1.005. CPA usually is 1.005 kilojoule over kilogram Kelvin, and the CPG is equal to 1. In this case, in this question, is 1.14. For the question from the textbook, if you look at the problem, it's already stated right here. I think the value is, yeah, this one. For the textbook problem, always use this value. For test question, always follow what is being recommended in the question. Okay, this is all the, but you can still use the same value. It does not make any much difference. Tapi macam for this case, take what I have mentioned, I have written just now. Take the CPA 1.005 and the CPG as 1.14.
Nine 946.3.
946.3. Okay. Anybody? Same? Oh, ada dapat 0.4. 946.4 Okay. Then after getting your T6, what do you think that you will get next? Of course, your T6S, right? So by using the isentropic efficiency for the turbine, in this case is the turbine high pressure, so this should be the T6 minus T7, sorry, T5. T5 or T6? T5, right? T5 minus T6 divided by T5 minus T6. Which one is the longer line? The longer line should be T5 minus T6. Then the upper one should be T6S. Okay, you can see it when you look at the TS diagram. So 5, 6. So the isentropic efficiency is T5 minus T6 divided by T5 minus T6S. Salah. I got the wrong place for the T6. You see? Yeah, T6 TS. Sorry for that. Okay, so this should be T6. This should be T6S. From here, you will get your T6S.
Kita tengok efficiency dia 0.8.
Isentropic efficiency, yeah, 83. Yeah, high pressure turbine is 0.83. Low pressure turbine is 0.85. Compressor is 0.8.
920.5.
920.
Kelvin.
Okay. And then from KIV, get your P6 over P5. Or P5 or P6. Yeah, P5 or P6. Or P6 over P5, it's up to you. Okay, what is your P5 or P6?
Zero point 538.
Pardon?
0.538.
That is P5 or P6 or P6 or P5? 0 point?
Itu P5 over P6. Cek saya.
Tak, but it's okay. We need either P5 or P6 or P6 over P5. Doesn't matter. As long as you tell me that 0 point something is P5 or P6 or P6 over P5.
P6 over P5.
Okay. Because if you put P6 over P5, for sure you are getting 0 point something. If you put P6 over P5, you are going to getting 0 point something. P5 over P6 is you get 1 point something. Because you know that the pressure of 5 is greater than pressure of 6. Okay, so 0 point?
538.
5, give me 4 decimal point. 5, 3, 8. What? 4 decimal point.
0.537.
537. 0.537.
9.
9. Okay, so this is a P 6 over P5, okay? P6 over P5. Can someone verify that?
Same value.
Okay, thank you very much. So there we got the P6 over P5, okay? Now we are going to get, after T6, T6S, T6, then we are going to get T7, okay? So what is our T7? T7 is given in the question. So what is our T7? Convert to Kelvin, shows 750 plus 1023. Okay. So after T7, are we going to get which value? T8 or T8S? What do you think? Let's say we try to look at T8 first. T8 should be, we look at the isentropic efficiency for the turbine for low pressure, which is T7 minus T8 divided by T7 minus T8. Shorter line divided by longer line. So our longer line should be T7 minus T8. So this should be our T8S. So if you look carefully, this is given. But as for T8 and T8S, we need to solve either one first. Okay?
Sir,
For sure.
T8S bukan yang bawah tu. Lagi panjang.
Kejap. Oh yeah, sorry guys. This should be 8. This is 8S. Longer line, shorter line divided by longer line, this is S. Okay, thank you very much. Okay, so we cannot use this formula to either to solve T8 or T8S. Then we have another formula, isentropic expansion, which is a T8S equal to T7 P8 over P7. This is a gamma gas minus 1 divided by gamma gas. So in this case, we already have the T7. We already have the P6 over P5. Okay, and we have the overall pressure ratio. Then the possibility of having this P8 over P7 is there. Okay, so what we are going to do right now is to try to solve it with using the pressure ratio, which is the expansion for the isentropic case. So we are looking at what? We are looking at 7 to 8. The process of 7 to 8S. So let us look at the pressure ratio at the turbine side. The overall pressure ratio of the turbine side is the overall pressure ratio is P5 over P8. The overall pressure ratio at the turbine side is equal to the individual pressure ratio, which is P5 over P6, multiply the low pressure turbine is a P7 over P8. Then, if we look this pressure ratio, overall pressure ratio, this P5 over P6, we can look back, we have P6 over P5 right here, 0.5379. And then from here, we could solve for the P7 over P8, which we need in this equation in order to solve for T8S. So use this pressure ratio relationship. The overall pressure ratio is equal to the pressure ratio of the low pressure turbine, a high pressure turbine, multiplied by the pressure ratio of the low pressure turbine. Okay, so this is 9.5. This is 1 over 0.5379. Then you solve for your P7 over P8. So try to get your P7 over P8 right here.
5.11.
Give me 4 decimal point. 4.101.
101.
Then from here, you are going to get your T8S. You are putting here in this equation. Then you are going to get T8S.
Six, 8, 2.5.
6. How much?
8. 6, 8, 2.5.
Oh, okay. I need to verify that again. Okay, everybody, can you define your P6 over P5? Okay, 0.5379. And then look back your P7 over P8. Are you getting the same value? 5.1105? .1101. Anyone can verify that? Tadi dapat apa? Nilai T8S?
682.5.
682.5 Kelvin. Okay, anyone can verify that value?
Same value, Doctor.
Same value. Okay, thank you. So up to this stage, we already have all the temperatures. Okay, we have all the temperatures. So the first question is to get, let me see, what is the first question? Okay, the first question is to sketch your where is this question? Okay, the first question is to sketch the schematic diagram. Print screen. Yes. So this is the rest of the question. Sketch the schematic diagram of the plant and show the cycle on the temperature entropy diagram. We have done that. And then B, determine the temperature of the gases leaving the high pressure turbine. Determine the temperature of the gases leaving the high temperature turbine, which is the temperature of the gas leaving the high pressure turbine, which is the T6. Okay, in this case, the question for part B is T6. The temperature of the gases leaving the high pressure turbine. So this is T6. We have got the T6. The third question, calculate the required mass flow rate of the air to produce the net power output of 10 megawatt. So part C, we are going to get the mass flow rate. You know that the mass flow rate is equal to the W divided by W. This is W dot net divided by the W net. If you look at the unit, this is in kilojoule over second multiplied by kilojoule over kilogram. So we are W dot net divided by W net. Okay, and our W net right here, W dot net right here is given as 10 megawatt, which is equivalent to 10 multiplied by 10 power of 3 kilowatt. Okay, which is equivalent to this unit of kilojoule over second. So I'm going to put right here is in kilojoule over second. So we need to get the W net. What is the W net? As we look at the relationship between the shaft, okay, the second shaft, which is this one, W net is equal to W378 minus W12. Okay, so the W net is equal to W for our second shaft, low pressure is 78, minus the W for 1, 2. And this should be equal to CPG T7 minus T8 minus CPA T2 minus T1. So you get your W net. Once you solve your W net, then solve for your M dot. Okay, I think we have got all the value already, so you just put in. And then part D is to determine the work ratio of the plant. Part D, work ratio. What is the work ratio? The work ratio is equal to the work gross, the work net divided by the work gross. Work net divided by the work gross. And the work gross is equal to W56 plus W78. And this for work gross, okay, 5, 6, 7, 8, and this work gross 5, 6, 7, 8. That's right. And for the work gross for 5, 6 is CPG T5 minus T6 plus 78 is CPG T7 minus T8. So once you have your work gross, then you get your W, the work ratio. And lastly is to get the thermal efficiency. But E, the thermal efficiency is equal to W net divided by the Q in. The Q in should be the Q to the both combustion chamber. The first combustion chamber is Q 1, 2, 3, 4, 4, 6 plus the reheat Q 6, 7. Okay, the Q in is equal to CPG. Sorry, it's not 5, it's not 4, 6, it's 4, 5. This is 5. Okay, 4 to 5, that's right. So this is T5 minus T4 plus, this is CPG T7 minus T6. Okay, so we have all the value, then we could get Q in. So once we have the Q in, then the thermal efficiency is solved. Okay, so try to complete all the parts that have been asked. So any question, guys?
So I have a question.
Okay.
So kenapa dekat why the combustion chamber the pressure get closer? That means there is a difference in pressure.
Harun, can you repeat that? I cannot hear you clearly.
Wait, sir.
Your voice is jumping. Yeah, Harun, can you repeat that again?
Can you hear me, sir?
Okay, right. Can.
Sir, why there is a pressure drop in the combustion chamber, sir?
Who said there is the pressure drop in the combustion?
Just now in the question, they said neglect the pressure drop in combustion chamber something. Why there is a pressure drop, sir?
Pressure drop because of viscous flow. Any flow, any fluid, any liquid, any gas which has viscosity, it will cause pressure drop. Anything. Okay, of the viscous flow because of the friction in between the surface of the internal flow surface and the liquid itself because of boundary layer effect.
Oh, okay, sir.
That's
Thank you, sir.
That's why we have pressure drop.
Okay, sir. Thank you, sir.
But in our case, usually we will neglect the pressure drop.
Okay, sir.
Right. Thank you. Right. Any question? Any other question? Okay. So kalau tak ada soalan, you complete all the value try to complete and compare with your friends lah. I'm going to look into the last part of our gas turbine plant, which is the third modification. Okay, third modification. The first modification is to look on the multi-stage expansion and reheat. The second modification is to look on the multi-stage expansion with intercooler. So both of these is in order to increase the work net. Okay, so we are going right now is to have the third modification, which give us the increase of thermal efficiency. Okay, the increase of thermal efficiency. So if I could sketch a new sketch of this gas power plant, looking at a very simple cycle on TS diagram, I want to highlight about the temperature. Okay, let's say we look at the turbine side. So let's say this is our intermediate pressure. We're having the multi-stage expansion. So this is our first expansion. This is our actual expansion for the first stage. And then this is the second expansion of the second stage. Okay, so this is without having any reheat process. Okay, without having any reheat process. But if we have reheat, let's say this is our reheat, and then this should be our second expansion after the reheat process. Now let's compare the exhaust gas temperature. Okay, the exhaust gas temperature. This is the exhaust gas temperature with reheat. This is the exhaust gas temperature without reheat. So when we have the reheat process for multi-stage expansion, we are going to have a higher exhaust gas temperature. Okay, exhaust gas temperature. So this is a very wasteful process whereby we are going to reject the high temperature gases to the surrounding. Okay, to the surrounding. So what we are going to do next is to make use of this temperature which have the high energy content of the exhaust gas after expansion at the second stage turbine and after the reheat process. So we are going to have this energy content in the waste heat to be used as a regenerator to heat up the temperature of air after the compression process. Okay? The first thing that I want to show right here is the temperature difference between a reheat process without reheat. With reheat process, the exhaust gas to be rejected from the plant is higher compared to this without any reheat. And what are we going to do is to make use this energy content in this exhaust gas to heat up the air after the compression process. Okay? So what we are going to do, if this is our compression process, let's say this is our compression process, this is the outlet temperature of the compression process. So I'm going to erase this part. Okay. So what we are going to do is to look this possibility of using this heat. You see, this is the temperature coming out from the compressor. So if I can sketch the level of these two, right? So this is the energy content. Compare the air and the exhaust gas temperature. Let's say this is B. Now, the possibility of energy at B, the difference in temperature, right? You know that if we look at this QB, we can take the CP, T, let's say this is 1, this is 2S, this is 2, this is 3, this is 3S, this is 4, this is 5, this is 5S, and this is, 6. 1, 2, 3, 4. Undo. This should be 3, 4. S. Sorry for that. 4S. This is 5. This is 6S. And this is 6. There's possibility of the Q, right? Having the energy is QB. Okay. This is delta TB. This is CP delta TB. CP delta TB, where delta TB is equal to T6 minus T2. CP T6 minus T2. But I'm not sure what is the actual CP, because from 6, we know that this is exhaust gas. From 2 is CPA. We might use this as CP average. Okay, we might use the CP average, right? But if we look at the energy content of the possibility of having the heat transfer between these two gases. So right now, if I could put a heat exchanger, let's say this is the part whereby we have the heat from the exhaust gas, no, heat from the air. This is the part heat from the exhaust gas. So this is being put together adjacent to each other by a component called as heat exchanger. Okay, so what are we going to flow in right here is at state 2. This, let's say, we are going to exhaust at 2 prime. Okay, and then let's say for the hot gas, we are going to put in right here is 6. And we are going to have right here, let's say it's 6 prime. The exhaust gas, actual exhaust gas. Okay, and if we assume this heat exchanger is being insulated, so what we are going to have right here is the Q color, red color, Q 6 to 6 prime is equal to CPG T6 minus T6 prime. And if we put in terms of the energy transfer, which is Q dot, then we have to add up one parameter right here, which is M dot. Again, for the air, this is for the air part, which is Q from 2 prime, 2 to 2 prime, which is equal to CPA T, right? In this case, T2 prime, higher temperature, minus the T2. Because of this heat exchanger is being insulated, okay, being insulated, sorry, before that, if I look in terms of the energy transfer by mass, then I have to put this mass in. You see right here, the m dot and the m dot here is the same because we neglect the mass flow rate of the fuel. Okay, we neglect that. Right. This is what happened. Okay, this is what happened. Then if we have this is equal and this heat exchanger is operating with 100% efficiency, then our T6 prime should be equal to T2 prime. Okay, if this is 100% efficiency. Right. Now, let us look at the increment of the temperature. Let's say this is not 100% efficiency. Okay, we don't have 100% efficiency of heat exchanger. Let's say that it has less than 1 or less than 100%. And let us look, let's say this is our 2 prime. Okay, which the T2 prime is not equal to T6 because of this efficiency that we have in the heat exchanger. So right now, this T2 2 prime is the process in the heat exchanger, or also known as the regenerator. Okay, and the actual Q that we have from the combustion chamber is from 2 prime 3. And this is the actual. For 4 to 5 is a reheat. Okay, a normal reheat. Okay, normal reheat. Right. So let us have the increment in temperature of this. Let's say this is SA. Okay, SA. So due to the inefficiency of the heat exchanger, we have the parameter called as the thermal ratio. For this heat exchanger, we have the efficiency of this heat exchanger called as the thermal ratio. And this thermal ratio, the definition is the available heat. Okay, this is the available heat, and this is the heat increment of the air. So what is the thermal ratio? The thermal ratio is the ratio between the change of temperature or the temperature increment for the air divided by the possibility maximum increment of the temperature of air. Okay, this is the maximum available, meaning that if we have a maximum thermal ratio, meaning that the 2 prime will be at the same level as T6 if we have the thermal ratio of 1. Okay, so in this case, we can elaborate the A as T2 prime minus T2 divided by the T6 minus the T2. Okay, this is the definition of thermal ratio. The increment, the temperature increment of the air after the compressor, which is A, divided by the maximum possible of the temperature, which is represent at B. So this is A divided by B. This is T2 prime minus T2 divided by T6 minus T2. Okay? So if we have less than 1 thermal ratio, then our 0.6, okay, this is 6 prime. Our 6 prime should be in between these two value, and usually we are going to sketch it at par as the T2 prime. So this should be our T6 prime. And we have another process right here that we have to sketch. So what is coming out is actually 6 prime from the plant. Okay, so this is the process 222 prime is the process of getting the heat from 6. Okay, and we have to get the thermal ratio, which is defined as A over B. Okay, guys? So that is a little bit on the using of heat exchanger or regenerator. Make use of the heat from the exhaust gas in order to increase the thermal efficiency of the plant. So we are going to continue this tomorrow, inshallah. So before that, let me take your attendance. So please check your chat box.